Thank you so much. So now we will jump a little bit to the early stage research, but at the end of my talk I also try to give a little bit of a vision what I believe that how can we contribute to the sustainability and bring some impact with early stage research. So in my group we develop holistic choices for multifunctional bio-based materials, and in addition to that we also develop interactive textiles, and we try to do methodology development for interdisciplinary work. So if there are people in the audience today who want to talk about these two other topics, please just interrupt me during the break times. But I've been running my group now for 5 years, and during these 5 years we've worked based on this hypothesis that pretty much anything that is made out of glass or fossil further polymers could, in theory, at least on paper, be replaced by biomaterials. And here are some of the examples that we've been working on. So as already mentioned, we do light management layers for photovoltaics, and there the interest is really in tuning the optical properties of the materials. We've been trying to do anything electronic. I will show some examples today. Then recently we've been also very interested in the acoustic properties of the biomaterials, and there will be a research stand at this event later today about this topic, so very much welcome to the research stand, everybody. And also we work on textiles, and later there will be a talk by Matteo and Sofia about this. All right, so let's jump to the early stage research. So nothing of this has been commercialized yet, but this is what we do at the lab scale. So first, I will go through 3 device examples, and if you want to think about them as simple terms as possible, just think about them as sandwiches. So for instance, solar cells, they are pretty much just a stack of different type of layers of functionalities, as you can see in this beautiful picture. And so you can think that it's pretty much a sandwich where you can replace different components with your favorite bio-based material. If you think about 3rd generation solar cells, such as the diasensitized solar cell here, so as we have shown in our recent review article, pretty much every functional layer in this stack can be replaced by a bio-based material if we want to do so. So of course then the good question is whether it makes sense or not, but technically speaking that's all doable. And today in my first part of my talk I will focus on the substrate layer, for which the main functionalities are transparency, because the light needs to go through to the solar cell, and then hopefully some added functionality that a bio-based material can bring to the solar cells. Okay, so this work started from this funny observation that when you wash your vegetables in your kitchen, different type of plant leaves have very different wetting properties. And we became very interested in the leek leaves, because when you wash leek in your kitchen, you can notice that the water droplets kind of roll into a preferential direction. So that means that the leek has this anisotropic wettability property. What we then did at the lab was that we developed this type of very easy soft lithography process where we can imprint the leek surface pattern on cellulose acetate. And then, because leek surface actually has a very hierarchical structure, we add one level of hierarchy by spin coating carnauba wax on top of the cellulose acetate. And here are the films. You can see them. And as you can see in this photograph here, they are highly transparent, so this was one of the key features that we need for the solar cells. Also, when you keep lifting them from the surface, you can maybe observe that the picture becomes a little bit hazy. So they have this interesting property called diffusive transmittance, and this can also be advantage when you need to collect a lot of light with a very thin film device. This was also something that we then noticed when we put these films on top of a perovskite solar cell. So thanks to both this diffusive transmittance and that they also exhibited anti-reflection properties, we could increase the power conversion efficiency of the solar cell below these substrates. Also, this added property was still there, so this is now the same property as on the leek leaves, but on a transparent substrate. So you can see this anisotropic wettability. The droplets start to roll onto a preferential direction, and they can then remove dirt or dust that has been accumulated on a solar cell. Okay, So this was my first case example. So then we will jump to another type of a sandwich. This is this type of a, this time this is much easier sandwich because it's symmetric. So we have symmetric supercapacitors. And the idea in these simple energy storage devices is that you just have two current collectors, and then in between of the current collectors, you place two electrodes that are separated by a thin layer called electrolyte, or the separator layer. And the function of that is not to let the two electrodes touch, so that will prevent the short circuiting of the device. So a few years back, this was work done when Finceres was starting. So we showcased with a bunch of nice people that pretty much all components in a supercapacitor can be derived not only from biomass, but pretty much from bio-waste. So for the electrode materials, we used animal bones, slaughter waste, so you can just pyrolyze it, you go to porous carbon, and that worked pretty nicely as an electrode. Then for the electrolyte, we applied brewery waste. We extracted cellulose nanocrystals out of the brewery waste, then ionically cross-linked it, and then made this sandwich. And now when you look at the functional properties of these sandwiches, so what was really nice is that they are highly bendable, so you can go down to 90 degrees and back, and as you can see in this figure, the performance of these devices is pretty much unaffected by this bending. And here in the other figure, you can also see that it's quite easy to handle these nanocellulose electrolytes. Now, this is a bit more recent work from this year. So we've been now optimizing more of the electrode materials, again, by using a cellulose nanocrystal ionically cross-linked gels. And here in this paper, we showcase that we have a very fine control over the porous carbon electrode structure. Okay. Third case example, also very early stage research, wearable capacitive pressure sensors. Here, very much conceptually similar type of an idea. We have, this goes too fast. We have here, again, a sandwich, which is again symmetric. So you need two substrates that are electrically conductive, and then a porous dielectric layer that goes in between them. Now, when you squeeze this type of a device, the overall capacitance changes, which can then be converted into a pressure signal, and the exerted pressure can be measured. So what we did here, our goal was not, again, just to use bio-based materials, but in addition to that, make the whole device biodegradable as well as edible. So we kind of limited the material choice based on these demands. And what we did here was that we made substrates out of cellulose nanofibers, and then we developed this type of a conductive coating out of carbon aerogel particles, and then just edible natural wax and vegetable oil. And this worked pretty well. It's easy to spread on a relatively rough CNF films. And then the remaining task was pretty much how to optimize the dielectric layer in between. Here we had a few different bio-based alternatives, and out of these, we were the most interested in these fruit peel-derived pectines. And here you can see a freeze-dried anisotropic cryogels of the pectines that actually worked quite nicely in these wearable pressure sensors. Here you can see them in action. So what was interesting in this concept that we developed was that these pressure sensors actually respond to a few different pressure regimes, so they can then be quite multi-use in human motion detection applications. For instance, we can use them for measuring the joint motion. So if you just move your finger, you can see how the capacitance changes here. But also, they work as well in these type of a bit more heavy-duty applications. So if you tape them in bottom of your shoe, you can also measure the pressure exerted by your heel when you are stepping on them. So it's as is shown here. Okay, so this gives a bit of a vision of what these could be useful for. So we showcase this type of a wearable keyboard application that you can use. And of course, since these are both biodegradable and edible, there is this speculation that maybe these are useful for gastrointestinal monitoring. And I know this is a speculation, so we are very far from the actual showcasing of this. Okay, so these were my 2 case examples that I wanted to walk you through. And now to the part of my talk where I want to make a little bit of, or like maybe raise a little bit of discussion of what we can actually do as early stage researchers. So of course, as I have said, pretty much everything can be done based off biomaterials, but then the important question is, when does it make sense to do like that? And this is now a work in progress, that what we are doing is that we're trying to build this type of scenario building tool. So we look at our applications and we look at different functional layers, and then we try to look for different applications, what are the actual volumes of biomaterials that are needed, and what are the tolerance of these different functionalities to the material heterogeneity. Since we know that many of the biosources are very heterogeneous, we think that it's very important to classify which of the applications are actually tolerant to that and for which high purification is necessary. And so by this, we try to then match different type of material streams to different type of applications to be able to build a bit more viable and better justified cases for the next TRL levels. So this is, as I said, a tool under development, so I'd be very curious to hear your comments and discuss this later today. Also, just a few thoughts based on this. As I have shown, we believe that it's possible to build up these scenarios based on good matching of material sources and different type of functional devices for future uses. But I also want to very much make the point that we don't think that just replacing things by biomaterials is equal to sustainability. Not at all. That would be very naive to think. So what we think is that much more multidimensional understanding would be needed for reaching real sustainability. And also, we are developing this type of interdisciplinary methodology so that we could actually involve more social sciences and other players in the field for this. Also, maybe another remark that I want to make is that sometimes bio-based materials really can bring added value, as we have shown in this solar cell case. Okay, so here are the talented contributors who contributed to this presentation. And then with these words, I want to thank you for your attention.
Thank you so much, Jaana. Very exciting and inspiring research. Do we have questions from the audience? We have a question from the chat. So, very interesting to take cellulosics to energy storage and harvesting applications. Are there companies producing solar cells or batteries interested in increasing the sustainability of their products?
Yes, absolutely. For instance, this Geysir Batteries is one company in Finland that has been very interested in looking different type of bio-based sources for both electrodes and electrolytes in them.
And what about the substrate, the top layer that you were talking about with the leak structure? Is it fully hydrophobic?
Yes, it is super hydrophobic, and also it has this anisotropic wettability, so you can kind of guide the droplets to one direction. So in theory, it could also be used for some kind of water collection applications.
Excellent. Thank you very much, Jaana.